Alright, hello everybody. Today we're going to be taking a look at, I think I'll split this video into two different dynamic programming problems. Dynamic programming is a topic that I haven't covered here for a while, but I thought I needed practice with it, so I'm making two videos on it. Alright, so let's go and read through this first problem. Given two string/text sequences, find the length of their longest subsequence that appears in both. A subsequence does not need to be contiguous, but must maintain order. So the definition of that is pretty clear. Well, not pretty clear, but it's important to realize that, for example, if we have these two strings, ABC, BD, then the string BDCAB, there are two possible longest common subsequence. One is BCAB, and that's because in this string one there's BCAB here and there's BCAB here. So you see how the strings aren't exactly next to each other, but they're kind of separated. So there's BC here, AB here, BCAB here, but they have to be in the same order from left to right. And BDAB, they're also BDAB. They're both also in common in these two two strings, and the output that we're actually returning is the length of the subsequence. So we're going to be supposed to return an output of 4. So that's the problem. Hopefully you guys clearly understand what the problem is asking for. Now, how are we going to go approach doing this? One thing we can immediately see is that if we see that both of the characters are matched, then we can add them to the LCS that must be part of the longest common subsequence. So we could just obviously go through both of the strings, and we basically start our entire process once we find a match. So once we find a match, we do this. Next, since we're going to be using a dynamic programming style approach, we are going to build a DP table, and we're going to be using a method called tabulation, which is a bottom-up method, which essentially what this means is that we're going to take this large problem, and this large problem can be categorized as a bunch of different little subproblems, and those subproblems are simply each individual character that we're going through repeatedly. And what we're going to be doing is we're going to be storing the results of the subproblem and then comparing them to each other. So we see that for example, B and B, when we get a match, that can be considered a subproblem. We see the match here, that the C is the same in both of this. There's a C here and there's a C here. That's also considered a subproblem. And we can repeatedly do this because these strings both contain similar characters. Well, not because, but if the strings contain similar characters, we can repeatedly add them and build them to each other iteratively in a DP table. So essentially we're going to be building the table iteratively. If the characters match, we're going to be adding 1 because 1 is obviously what we're going to be using to increment the final output, which is the length of the longest common subsequence. And then we're going to be taking the previous character in the list. So that's basically it, and that's only if the characters match. If we're not matching, we're going to be taking the maximum of skipping 1 from either string. So, and obviously the final output in a DP table tabulation approach is going to be the final value in the DP table. Since it's going to be a 2D DP table, it's going to be the bottom right corner. So it's that. Hopefully that explanation kind of made sense here. Let's take a look at how this kind of thing would look like. What we're going to be doing is, first of all, we got to make our function. Sorry for scrolling down. Def LCS. We're going to have str1, str2, so string 1 and string 2. These are our two inputs. The output is going to be a string. But what we're going to be doing is first, we're going to be taking the length of these two strings. We can put them into two variables. Let's call them n and m. So n comma m equal to length of string 1 and then comma length of string 2. And how we're going to be making, what we're going to be using these for is to make the DP table. So the dynamic programming table that we use for tabulation. We're going to have it be filled with zeros because obviously the base condition, if you guys could figure, if there's no common thing, there's like the longest common subsequence is nothing. It's just going to be returning 0. So we're going to start by assuming obviously that every single possible, there's no common subsequence at all. So we're going to do 0 times the length of string 1 and then the length of string 2. So for the columns, this is going to be the columns m plus 1. How do I do this? The parentheses m plus 1. M plus 1. And to loop this, we're going to be looping this for each row. For x, it can be any variable, range of n plus 1. So basically, we're going to be making this many rows and this many columns, basically. So actually, no, sorry, this many columns because this is the list, the first list that we're making. The top row is going to be this many columns multiplied by this many rows. And it's actually going to be rows and columns plus 1. That's also an important thing to mention. It's not exactly going to be the length of the string. It's going to be the length of the string plus 1. And the reason why is we're going to be starting from the first element, not the 0th element. We're going to be starting from the first element. So here's how we're going to be looping through this string. It's going to be starting from 1. So we notice we're going to be starting from 1 to n, so the number of rows. We're going to be looping through the rows, and then we're going to be looping through the columns. Starting from index 1, which is the second element of the DP table. And what we're essentially going to say, we need to check to see if the two values are equivalent to two characters of the strings are equivalent to each other. So all we're going to do for that is we're going to say str1, so string 1, the string 1, you can index into a string in Python. I think you can in most languages. You could choose the index of I minus 1, and as you know that I minus 1, it's since we're starting from the first index, I minus 1 is always going to be 0, which is why it goes up until n, with the length of n. It'll always go up in that. And basically what we're saying is if it's equivalent to string 2 of j minus 1, since we're looping through for the columns, for the column, m is actually the rows, my bad. For the rows, if we're looping through string 2, if we see them equivalent, then essentially all we're going to be doing is we're going to be saying that, like I mentioned, we're going to be setting that value in the DP table defined by ij, because that's where we are right now, is equal to 1 plus the previous value. So the previous value is actually going to be I minus 1, j minus 1. And if you can visualize this in the DP table, what I minus 1, j minus 1 is essentially going to be in the top left corner. So if we see that the two strings are equivalent, we are going to be setting the current value at which we are at to be equivalent to 1 plus whatever is in the top left corner of it. Otherwise, so what do we do if they're not equivalent? So if they are equivalent, we know that we got a match, so we want to increment the increment the size of the least common subsequence by 1. Otherwise, all we are going to be doing is we are going to be setting that value to the maximum element. Why are we going to be doing the maximum element, and what are we going to be doing the maximum element of? What we're actually going to be doing is we're going to be setting it to the maximum element of the top I minus 1 of j. So you know how I is indicated by the rows, which is n. This is indicated by the rows. So dp of I minus 1 and j is actually, I'll probably put this out, a visual representation is a little bit better here. So our dp table will start something like, it's a little bit hard to explain. No. The dp table will look something like this, and essentially when we're setting this, let's say we find a match at this this position here. Right now there isn't a match, but assuming that there is a match, essentially what we're doing is that the top value, we're going to be taking the maximum value of the top value and the left value, and if we find that the maximum value of that, then we set that to the current value, only if the characters are not matching. So the reason for doing this is kind of a little bit hard to explain. It involves a lot of logical understanding, and we could do a step-by-step example, but for simplicity's sake, essentially all we're doing here, is we're taking the comparison between the top element in the dp table and the smaller element in the dp table. So this would be dp of and the left element. So we're comparing this one to this one, and we're taking the maximum value of that, and we're setting the current dp value to that value. Okay, so hopefully that explanation was a little bit clear. And then at the end of this loop, we can simply return dp of n at m. And yeah, that's basically it. N and m are of course the lengths of the strings. And yeah, that's essentially how you solve the least common subsequence of the string in using dynamic programming tabulation. So we could take a look at the test. So for example, if we did everything right, for this code, we should get the output of 4, similar to the example. So let's test this, run the code, and we do indeed get 4, because the longest common subsequence between these two variables is going to be AB, not AB, it's going to be either BDAB, so BDAB what we have over here, or it could also be the, what do you call it? We found one earlier. There's I think it was yeah, it was BCAB. So BCAB and then BCAB. So those are the two possible longest common subsequences, and both of those show an output of 4. So this one would be 4. You could also take a look at this. This is another test case. For example, the longest common subsequence of this would be GTAB, which is in here, and it's also G, and then there's a T, and there's an A, and there's a B. And the output should also be 4 on this problem, and we also get 4. So that's essentially how the least common subsequence problem works. the code and the core logic as to why we want to focus on the left and right, the um, top of the DP tables is a little bit complex, but essentially what we're doing is we're checking to see if the characters are even. If they are even, we're incrementing the least common multiple count. Otherwise, we're going to be taking what do you call them, the maximum value of skipping one character from either string. So the maximum value of either string. So yeah, that's essentially how this problem works, and I'm going to be doing one more in the same video. Stay tuned for that shortly. Alright guys, here we are back again. Here's the second dynamic programming problem that we're going to be solving today. This is called the knapsack problem. So, this is what the problem description is. You are given n items, each with a weight wi and a value vi. A knapsack with a maximum capacity w. So we have a knapsack, and what we're essentially trying to do is we're trying to find the total value that we can put into the knapsack without exceeding the weight limit. So we're like in an imagine we're like in a room filled with treasure, and we're trying to fill whatever sack we have with the maximum possible value worth of jewels or treasure or whatever we have with the limited capacity that we have, assuming that we're given two lists. So let's have like a sample input. Let's say we have like a sample input that's something like this. Usually I do this beforehand. Oh, sorry, don't ignore this example of this. So let's say we have the values of this. Essentially what we're trying to do is we're trying to find the most possible value that we can get out of the knapsack if we can only carry 50 pounds. So since we can only carry 50 pounds, we know that we want to get this one worth 30, this one worth 20, so we can get a total value of 220 from these two items that we can get here. And that's the maximum possible value we can derive from this possible list. So how are we going to approach this type of problem? What we're going to be trying to do is we're once again going to be using tabulation, where we work from the bottom up. We're going to split this up into smaller sub-problems. We're going to figure out a base condition, and then we have two decisions. So for example, when we stumble across an item, let's say this item, 60, 10, so it's a value of 60 and it's a weight of 10, we have two options to either include it or exclude it in the knapsack. So those are the two situations that we essentially need to account for. Do we take this or do we not take it? And we're going to be building the DP table. This one is going to be a DP table of IW. It's going to be a 2D list that is going to be based off of the values, and it's going to be given the n items and W capacity. Basically off of those two row column structure, we're going to be finding the most possible value from it. So let's start by going through and seeing exactly how we can approach this, how it would look like in the form of code. So def knapsack. Hopefully you guys don't hear some notification pings that I'm getting. Don't worry about those. Weights W. So we have those three things: values, weights, and the capacity of the knapsack. What we're going to be doing is we're going to be creating a DP table. One thing we're going to do is set this value n values, which is going to be the number of rows that we have in our DP table. It's going to be the length of the values. And to create the DP table, it's very similar to what we previously did for the previous problem. we're going to be filling it up with 0 because the base condition, just like the other problem, is if the knapsack capacity is going to be 0, there's basically nothing. So we're going to assume that the least possible value that we can get is when the capacity is 0 and we can't fit anything into the knapsack anymore. So that's going to be 0. And we're going to be filling it out for W plus 1. If you remember, W plus 1 is representing the capacity. Remember, in these kind of problems, we always set keep the first absolute first value 0 0 as our base condition, and then we're going to be saying for x in range of n plus 1 actually. What did I do wrong here when creating this? Times w plus 1. Oh shoot, I meant to say dp is equal to. So this is how we're going to be making our dp table, tabulation table, two things with the number of columns represented by the capacity and the number of rows represented by the values, the length of the values. So we have that dp table created, and all we're going to be doing is we're going to be filling it up by having we're going to be looping through first the rows and then the columns for the capacity. And we're going to be once again starting from the first index and going all the way towards the end with our the final output we're trying to solve is going to be the final solution, which is going to be dp of nw, which is the last bottom right value in our 2D array that we create. So w plus 1, the uppercase W. Alright, now what are we going to do? So remember, there's going to be two options. So we can start by making a if-else statement, and the else condition is pretty simple. The else condition is what happens when we don't want to take the taken item into our knapsack. So if we don't take an item into the knapsack, all we need to do is set our value, our current position in the dp table as dp of I minus 1 w. And this is previously, if you guys remember, I is represented by the length of the values, so I minus 1 is the previous value that we checked. So essentially what we're saying is if we're not taking it, all we're doing is we're setting the current new position that we're at in our dp table to the same as our previous one, because we're not changing anything. So that's what the I minus 1 is indicated by. Otherwise, we are going to change it to, what we want to do is we want to see whether or not we can improve the value by taking the thing and adding it to the knapsack. So we're going to be using a maximum function, and we're going to be using the maximum function. Wait, 1 second. The condition, I should have probably specified this first, is if the weights of the previous value, so we have this weights list right here. If weights of the previous value that we're in, I minus 1, is less than or equal to w, and w being where we are right now, the current capacity that we're on right now. So if we see that there's an item that can be fit into our knapsack, essentially, that's what this means. If the capacity is open, if we can fit the whatever weight we have in our list into the knapsack, all we need to do is take the maximum value of, remember, the previous value, so I minus 1 w, just like we have here, or instead we're going to be adding two things, values of I minus 1 plus, what is it again, plus dp of I minus 1, so the same what do you call, same I, which is the same row, so we're going to be on the same row, that value of w minus weights of I minus 1. So essentially right here, that weight that we calculated here, we're going to be adding that column in the previous row. We're going to be adding that column, the column's row value, to the previous value, essentially. And we're going to see if that value that we have is greater than the previous value that we do. And if it is, then it is an item that it is worth taking into our knapsack, essentially. So at the end of this loop, we can essentially just return out dp of nw. And it's important to mention, I don't know if I mentioned it in the last one, I should probably mention it here. In this situation, the time and space complexity is going to be calculated by the time of it's going to be n times w. So as we see, it's an n squared solution with it being n times w. And it isn't necessarily n because it all depends on the constraints of the problem. If the capacity was much lower and the value in the values, if the length of the values was much greater, the number of items that we have is much greater, then it could be a very high time complexity. If the capacity is very low, it's going to be a lower time complexity, obviously. But that's essentially the time complexity. It isn't quite n squared, but it is close to that. So that's what the time complexity of this dynamic solution, and the space complexity is obviously the same since we're making a 2D array. The 2D is the length of n times the length of w. So that's what the time and space complexity of this problem is. And yeah, that's essentially how the knapsack problem works. We can take a look to see this thing. So let's say we have these values is equal to something like this, weights is equal to this, and let's say the capacity is 50. What we want to see is the output of 220 by adding these two values together. That fills up the knapsack. So, and there we go. We see the maximum possible output of 220. So yeah, hopefully you guys understood that knapsack problem. Hopefully I understood it. I think I did a decent enough job of explaining all the logic of including and excluding the item in the knapsack and adding it to the knapsack. And yeah, that's pretty much it. And I'll see you. It was a long video, especially considering that it's this problem along with the previous one that I recorded in a separate cut. So yeah, hope you guys enjoyed that video, and I'll see you guys in the next time. Bye.